I apologize for being so late. Are there any questions on the last lecture, the Feynman rules for theories involving fermions? Now if I can get this in order. Okay. Today we are going to discuss, for a Dirac theory, the famous discrete symmetries of nature, P, about which we've already said quite a lot, but I want to say a few more words, charge conjugation, and time reversal, although as always in a relativistic theory it's more convenient to discuss PT. And I will also prove, in the same diagrammatic way I proved it for purely scalar theories, the CPT theorem. Let me begin by discussing parity. When we discuss the theory of a single scalar field, we define parity as simply x going into minus x in the argument of the field. However, we realized that when we had a theory of more fields, we could have a more complicated definition of parity. It could be possible that the fields would mix up among themselves as well as the space point changing. And we gave several examples where I seem to have fallen into the papal we. I gave several examples where this matrix was diagonal. Some of the fields were multiplied by +1, others by -1. Of course, the same is true when considering spinor fields. It is possible, if we have a set of spinor fields, then we may not have the freedom to make individual phase transformations on each of the spinor fields, perhaps only on all of them collectively. There may be only one internal symmetry, not one for each field, in which case, to find a good definition of parity, we may have to mix the fields up among themselves, or if you diagonalize the matrix M, multiply the different fields by different phase factors. Oops, B. As an example, let me consider the theory of two spinor fields interacting with a scalar, a spinless field, with, say, the interaction, I'll call the first one capital A. So that that part would be parity invariant if A were transformed in the standard way, or the standard way with any phase factor, and phi were a pseudoscalar. Likewise for this part, but now I throw in an interaction without a gamma 5. This theory is parity invariant. Well, there are several definitions of parity, because still you can make simultaneous A-B phase transformations and everything is unchanged. But among other possible definitions of parity, this one works. A of x and t goes into beta A of minus x and t. B, however, has a relative minus sign in it, minus beta B of minus x and t, and phi is pseudoscalar. Of course, a possible definition of parity would also be any phase factor here. That would still keep things all right. But that's our usual ambiguity. Whenever we have both an internal symmetry and one good definition of parity, we have a number of definitions of parity caused by multiplying parity by an internal symmetry, which one we choose to call parity is merely a matter of convention. We would describe the situation by saying, perhaps, that the B particle has opposite intrinsic parity to the A particle. A state of two A particles in an S wave would be even in parity. A state of two B particles in an S wave would be an eigenstate of parity with eigenvalue +1, but a state of an A particle and a B particle would be an eigenstate of parity with eigenvalue -1.
You say that beta is supposed to be safe factor?
No, beta is the gamma naught.
Oh, yeah.
A and B are four-component spinors. Are there other questions? I talked about the intrinsic parity of two kinds of particles, but one thing I didn't discuss in my discussion of parity was the intrinsic parity of a particle and its antiparticle. For a charged Bosch field, of course, the particle and the antiparticle have the same parity. Whatever happens to the particle, whether it gets a plus sign or a minus sign, the antiparticle gets the same. Phi and phi star have the same parity transformation laws. What has happened for a Fermi theory? Well, parity acting on the fields is a multiplication by beta. And of course, the particles are associated with the fields via the expansion of the fields in terms of annihilation and creation operators, which tells us how the unitary transformation associated with parity acts on the creation and annihilation operators, and therefore on the states. Now let's begin by taking the factors that multiply a state at rest. If I take a state at rest, beta on U0 var is, of course, U0 var. But beta on V0 var is minus V0 var. By the known commutation properties of beta with the generators of Lorentz transformations, which we use to define the UPs and VPs in terms of the U naughts and V naughts, beta on UP of R is U minus P R, and beta on VP of R is minus V minus P of R, because beta turns commuting beta through boost operator changes the direction of the boost, since beta anti-commutes with alpha. Thus, if we have the unitary operator that affects parity, acting on free particle states, or as you will, on in and out states, if we're talking about an interacting theory, will turn a state of one nucleon, and this is a nucleon. I don't have any notation to tell you that. It's a nucleon of momentum p, not an anti-nucleon of momentum p, into R minus P, where R is the index telling us which creation operator is used to create that state. Whereupon, acting on a state of one anti-nucleon, unfortunately, with the notation I've developed so far, that's exactly the same state. Oh, I can do it better than that. Hold it, I was sleepy when I wrote the lecture last night. There, that's the good way of doing it. That is to say, parity has its usual properties that it has in non-relativistic quantum mechanics. It changes the sign of the momentum but does not affect the spin. However, It has opposite sign for nucleon and antinucleon. Nucleon and antinucleon have opposite parity, and thus, for example, nucleon and antinucleon in an S wave is parity minus. Whereupon nucleon and nucleon, or antinucleon and antinucleon in an S wave would be parity plus. This has strong experimental implications if you are doing, if you are, of course, dealing with the parity conserving theory. As an example, let me consider the process proton plus antiproton annihilation goes into pi plus pi minus at rest. That means the proton and antiproton are at rest, the slow antiprotons which are sending into a block of ordinary matter, for example. We know from non-relativistic quantum mechanics that such exothermic reactions at small velocities of the incoming particle are dominated by the S waves. This, of course, is perfectly also true in relativistic quantum mechanics, since the argument is simply that if there is no spatial momentum, there is no spatial angular momentum. If P vanishes, R cross P vanishes, and that has nothing to do with relativity. Therefore, at rest, the process is dominated by S wave, and therefore there are two states, L equals 0, J equals 0 or 1. The two possibilities for the value of the spin. Both of these states, by what we have said, are parity odd, eigenstates of parity with eigenvalue -1. Parity does not affect the spin, it just affects the momentum. Pi plus pi minus are particle and antiparticle and bosons. Therefore, they have the same intrinsic parity, whatever it may be. It turns out the pion is pseudoscalar, and that parity is minus, but that's irrelevant. So this can go, a J equals 0 state here is necessarily, since it's two particles, bosons, is necessarily parity plus. The J equals 1 state is necessarily parity minus. And therefore, if one were to do the experiment with a polarized target and a polarized beam of antinucleon coming in on it, in the state which was spin, the state which was total spin 0, the 2 pi minus decay would not run, whereupon in the state that was total spin 1, the 2 pion decay, 2 pion production would not run. It only runs from the total spin 1 state. The J equals 1 state, J equals 0 state is forbidden by conservation of parity. Therefore, only this one is allowed to make pi plus pi minus. The others must make, or indeed any two particles of the same intrinsic parity, any two bosons, pi eta, for example, is also forbidden. The J equals 0 state typically goes into 3 pions, in fact. Are there any questions? I mean, this is to demonstrate that what I have derived is not a formal conventional thing, but something that actually yields experimental consequences.
You said pi plus and pi minus have opposite?
No, they have the same. They're both parity minus. They're bosons, and therefore particle and antiparticle have the same intrinsic parity.
Well, then doesn't the pi plus pi minus also have positive parity? Plus parity? And you say that
Plus parity if L equals 0 and minus parity if L equals 1. If I have two particles in an angular momentum state, the parity is the product of the intrinsic parities times -1 to the L. They have no spin, so J gives me L. Okay, is there people who are confused about this point? I assume you know some high-energy phenomenology on an elementary level, but if you don't, I'll be happy to explain anything that's puzzling you. That concludes what I wanted to say about parity. I will now go on to the discussion of charge conjugation. Let me again recall what happened in the theory of a scalar field, a charged scalar field, a complex scalar field. There, our starting point was this theory of a free field, where we observed that the wave equation was real, the Klein-Gordon equation was real, and therefore if psi was a solution of this classical field equation, so was psi star. And we found a unitary operator charge conjugation that implemented this, invariance in the quantum theory. Now we have to deal with the Dirac equation. And the obvious question to ask is, is there a similar invariance here? I write psi star rather than psi adjoint, meaning I will take the complex conjugate of each of the four components of the Dirac field, but I will not turn a row vector into a column vector, or I should say I will not turn a column vector into a row vector. Likewise, when I discuss the quantum theory, I will use star to mean I take the operator adjoint of each of the four operators, but I do not turn a column vector into a row vector. I'm sorry for that notation, but our other notation is too complicated. I have no other symbol to use for just adjoining the operators and not turning row vectors into column vectors. Now, the answer is this true? And the answer is, it depends on the representation of the gamma matrices. Yes, if we can find a representation of the gamma matrices in which the gamma matrices are all imaginary. Of course, if we could find such an invariance in such a representation, we would be able to find a similar invariance in any other representation just by making the right transformation, but then there would be a matrix intervening here, and charge conjugation would not look so simple. The question is, therefore, do such representations exist? They do. I will write one down for you, chosen essentially at random, just to demonstrate they exist. Their utility was first pointed out by Ettore and Rana, and they're called Majorana representations. Now I will demonstrate the existence of a Majorana representation by constructing one. That is, constructing a set of four gammas that obey the proper algebra and that are all imaginary. I constructed one essentially at random. The trick is just to write down our original standard representation alphas and betas and shuffle them around and put i's in certain places so that everything obeys the right gamma algebra. Thus, gamma naught will be 0, sigma y, sigma 0. That's one of our original alphas, alpha y. It has square 1, and it's a Hermitian operator. Gamma 1, I'll choose to be I, 1 minus 1, 0, 0, all in 2 by 2 block form. That's our original beta with an I in it, so it'll have square minus 1, as gamma 1 should have. Gamma 2 will be I, 0, sigma z, 0. That's our original alpha x, again with an I in it to give it the right square. And gamma 3 will be I, 0, sigma x, 0. They all have the appropriate squares, plus 1 for gamma 0 and minus 1 for the other 3. They all anti-commute with each other because they're just our original alphas and betas reshuffled. They all have, and therefore they are a representation of a Dirac algebra, and they're manifestly all four of them imaginary. There are several advantages before I turn to this charge conjugation. So we can do it, and of course this one is just one of an infinite number of others. Any real similarity transformation will also preserve the Majorana property. So it is possible, and therefore there is such an invariance, at least on a classical level. I would like to write down some general features that follow from being in a Majorana representation that will be useful to us later, not only here, but in our discussion of time reversal, which also looks simpler in a Majorana representation than it does in any other kind. Of course, once we derive things, I should emphasize, once we derive things in this particular restricted kind of representation, as long as we're dealing with representation invariant objects like psi bar psi, what we derive from them is independent of that particular representation. This is just nice if we're working about the properties of psi and psi bar individually. The Lorentz matrices have a nice property, which I will demonstrate, and in fact write explicit expressions because I will need them later. For d of lambda. In a Majorana representation, they are real. This reflects the fact that charge conjugation commutes with Lorentz transformations. I'll write down, just to convince you of this, I'll write down explicit expressions for the L's and the M's, and therefore what goes out of them. Let's take mz, which I remind you is I alpha z over 2. Alpha z is I gamma naught gamma 3 over 2. Since gamma naught and gamma 3 are real, are imaginary matrices, their product is real, and the I makes things imaginary. So, a useful fact, mz equals minus mz star, and of course, mutatis mutandum for all other components of m. The representation of a rotation about the z-axis, or sorry, a boost about the z-axis by an amount phi, hyperbolic angle phi, is therefore E minus I from the definition of how you get things from the m's, gamma naught, gamma 3, phi over 2, and is a real matrix. Likewise, as another example, let me take a rotation about the z-axis. Lz is by definition minus I mx with my, and it is a work of a moment, which I will not burden you with, although I have it written down here to show that this implies Lz is minus I over 2 gamma 2 gamma 3. So again, Lz is minus Lz star, and likewise for all other components. And a representation matrix for rotation along the z-axis by an angle theta is multiplied by minus I. So there I have e to the minus 1 gamma 2 gamma 3 theta over 2, again a real matrix. Of course, aside from the minus sign, you could almost guess this from this by Lorentz transformations. This is, after all, what represents a Lorentz
There's no I here.
No, there's no I. There's an I in here. This represents a Lorentz transformation in the 0-3 plane, and this represents a Lorentz transformation in the 2-3 plane. Whoops, did I write 3? That was a mistake. Horrors, perish forbid. What should I have written? 1, 2. 1, 2. Sorry. I had to get up early today to go to a noon committee meeting, and I'm a little bit foggy in the head. Also, I went bananas last night trying to work out time reversal, and I finally got it straight. Time reversal always makes people go insane, and I didn't get to bed until 5 in the morning. So you must suffer with these things. Good. Now, let's go on and work out the what time reversal does, what charge conjugation does to the actual solutions of the free Dirac equation, the u's and the v's. The solutions to the free Dirac equation obey this equation. Now we are working in a basis where gamma mu is imaginary, and we don't have an I in front of the d slash, it's just a p slash. Therefore, if I take the complex conjugate, this term changes, the p slash term changes sign because it's imaginary. Therefore, this is a v-type solution. And since everything commutes with Lorentz transformations, which tell us how to connect u's and v's for different values of p, once we've connected them for p equals 0, we can, with a clear conscience, adopt the convention that VR of p is UR p star. Just to check that this is consistent with our idea that the charge conjugation doesn't change the value of the angular momentum or anything like that. Let's take a particle at rest and look at U10, which is supposed to be an eigenstate of L sub z with eigenvalue plus 1/2. As we see from the central board, LZ is a pure imaginary matrix, and therefore when I take the complex conjugate of this equation, LZ U10 star equals minus 1/2 U10 star. That's right, because as you recall, it's the U that is an eigenvalue of L sub z with eigenvalue plus 1/2 that's associated with the annihilation of a particle with z component of angular momentum plus 1/2, but it's the V that's an eigenstate of angular momentum minus 1/2 that's associated with the creation. Did I say creation before? I meant annihilation. The creation of a particle, I suffer from these binary confusions, you must forgive me, that's associated with the annihilation of a particle with L sub z equals plus 1/2. The creation of a particle with L sub z equals plus 1/2. The sign flips because one's got a creation operator and the other's got an annihilation operator. As you may remember from our earlier discussion of felicity of neutrinos, where we went through exactly the same routine with exactly the same incredible confusions on my part. Stop it. You all know it. Otherwise, ask questions. Save me. Help. Create a distraction.
Do you
Now,
expect that to be true in all representations?
hmm?
You know, that
No, but no. Oh, no. Not this. This is for my Rana representation. A general representation, there'd be some matrix intervening, but that matrix would also work its way out through here. Okay. We'll see it. Well, you'll see it happening. We'll eventually end up with unitary operators acting on the B's and the C's, which are independent of this. Therefore, with this representation, we can write out the expression, the usual boring expression for the free field. Sub P, a nucleon annihilation operator times a free field wave function times e to the minus I p dot x plus CPR adjoint times a V, which we now recognize in our Maya-Rana basis is U star, times e to the I p dot x. Likewise, psi star, not the bar, but the star, sum on R, integral, ditto, and I left out the 2 pi to the 3 halves. BPR adjoint, UR of P star, e to the I p dot x. I've just complex conjugated everything, but not turned, Commission adjointed everything, but not turned row vectors into column vectors, plus CPR unadjointed, UR of P unstarred, e to the minus I p dot x. Okay, that's the definition of the adjoint. Thus I see that if I define a, please notice this term is the same as this term is the same as this term, and therefore if I define a unitary operator, U sub C, such that U sub C adjoint BPR U sub C equals CPR, obviously defines a unitary operator acting on the many particle states. If you put in the reasonable additional condition that it leaves the vacuum invariant, and UC adjoint CPR UC equals BPR. Then by applying, and of course, likewise from the adjoints, by adjunction, by applying these operators to this equation, I instantly deduce that UC adjoint psi of x UC simply exchanges this term and this term, this term and this term, equals psi star of x. See the tricky way things work out. You might have been a little worried when I found complex conjugation turned the positive frequency solution into a negative frequency solution. You would have thought, oh, we're going to get something that changes annihilation and creation operators. It doesn't happen that way. Annihilation operators stay annihilation operators, creation operators stay creation operators. Any questions? Now, so much for the free field. And therefore, this unitary operator, as you can easily demonstrate, commutes with the free field Hamiltonian, since a particle state and an antiparticle state have the same energy. If you write the Hamiltonian in terms of annihilation and creation operators, it's obvious. To discuss an interacting theory, we have to discuss the charge conjugation properties of the various combinations of fields that enter into defining the interaction to see whether or not they commute or fail to commute with this charge conjugation operation. Therefore, since most of the interactions we will deal with will involve the fundamental 16 quadratic forms built up out of a psi and a psi bar. And even if you're dealing with more complicated things involving 2 psis and 2 psi bars, that can be usually as writable as a product of such quadratic forms. In fact, invariably writable as a product of such quadratic forms. We'll really have to deal only with entities of the form A bar MB, where A and B are perhaps 2 different Dirac fields, and M is some 4 by 4 matrix, either 1 or gamma 5 or one of the 4 gamma mu's, etc. I will assume that both A and B have the charge conjugation properties I have written down. Of course, when I'm dealing with more than one field, everything I said about parity in this context is also extendable to charge conjugation. There are cases in which theories do not look charge conjugation invariant if you give everything the same phase factor in charge conjugation, but by putting an extra minus sign in front of one of the two fields, you can save things. I shan't bother to work that out here. I'll work out the charge conjugation properties of the quadratic forms, assuming everything has this charge conjugation property. And I presume you have enough wit yourself to figure out what happens if I put in a minus sign in one of these. Now, it's I actually want to study things in a quantum field theory, and I will assume that this is an object, say, occurring in the interaction picture, interaction Hamiltonian, so I can normal order it and not have to worry about delta functions coming about when I switch the two operators if they're identical. Equivalently, I can say that this is an object built out of those funny anti-commuting fields that are the objects that appear in the classical theory of Fermi fields. And that has, of course, the same combinatoric structure as normal ordering. When I switch the two things, I get a minus sign. That's going to be important later on. Otherwise, we get a wrong answer if we didn't keep account of that Fermi minus sign. A bar MB equals A adjoint gamma naught MB equals, well, let's see, I worked it out very nicely. Right, that's as far as I want to go. Therefore, when I apply, I'm sorry, I'm a little bit sleepy. I'm trying to think, what did I do at 4 in the morning when I was awake? Okay. Now I apply the charge conjugation operator on the right and the left. That's a unitary operator, of course. These are just numbers and are totally unaffected. B goes into B star. A goes into A adjoint goes into A transpose. Adjoint is transpose conjugate. Now, this object is not in a particularly nice form to combine together again as an A bar B, but it is in a nice form to combine together as a B bar A if we realize that every 1 by 1 matrix is equal to its transpose. Therefore, I can write this as B star transpose M transpose gamma naught transpose A. Except when rearranging these things, I not only have to do a matrix identity, I have to stick the B on the left of the A, and because of the definition of normal ordering, that gives me a minus sign. No, at the moment, M is anything. Any 4 by 4 matrix. What its Lorentz transformation properties are irrelevant. 4 by 4 numerical matrix. Okay. Now, gamma naught is a Hermitian imaginary matrix. We're always working in Majorana basis. So gamma naught is minus gamma naught. Therefore, this thing is equal to plus B adjoint, which is B star transpose, M transpose, gamma naught A. I will now insert a gamma naught here and a gamma naught here, and write this as B bar M bar star, because that's what this is. If it were the adjoint, it would be M bar, and I star to undo the complex conjugation in the adjoint, A. Thus, I have the general rule. I'll now write down the left-hand side again. You see A bar MB, UC adjoint, equals B bar M bar star A. Okay? That has the general structure of what you would expect charge conjugation to do. It takes a operator that annihilates a B and creates an A, and turns it into an operator that annihilates an anti-A and creates an anti-B. This is, I remind you, all special to Majorana basis, because, of course, what M bar star is depends on whether things are real or imaginary. That depends on what basis you're in. Thus, we can work out the 16 quadratic forms just by using this bar star rule. Question? Oh, no. Well, it doesn't matter. UC squared is 1 from the way we've defined it, but therefore, under charge conjugation, let's make a systematic table of all the quadratic forms. A bar B. M is 1, which is both self-bar and real. Therefore, this goes into B bar A. In other words, psi bar psi is even under charge conjugation, as you would expect, because it's a term that appears in the free Hamiltonian, which is a charge conjugation invariant theory. Yes. Thank you. Either normal ordering or classical anti-commuting fields. A bar I gamma 5, B. I gamma 5, I remind you, is minus gamma 0, gamma 1, gamma 2, gamma 3. Gamma 5 has an I in it. I gamma 5 doesn't. I gamma 5 is self-bar, and it is also real, because this is the product of 4 imaginary matrices. So this goes into B bar I gamma 5 A. Gamma mu. Gamma mu is self-bar, but it is imaginary. So this goes into minus B bar gamma mu A. Thus, psi bar gamma mu psi is odd under charge conjugation. This, again, should be no surprise, because, after all, it is the electric current, and we know that charge should change sign under charge conjugation, if anything does. The A bar gamma mu gamma 5 B goes into, well, now things are different. Gamma mu gamma 5 is self-bar, but gamma mu is imaginary, and so is gamma 5, since it's I. So this is a real matrix. So bar star does both do nothing. And this is, the axial vector current is even under charge conjugation. Gamma mu is imaginary, and so is gamma 5, right? Finally, the tensor invariant, A bar sigma mu nu B. Sigma mu nu is I times the commutator of two gamma matrices. Therefore, it is both self-bar and imaginary. And therefore, this is minus B sigma mu nu, B bar sigma mu nu A. Any questions? It goes into, thank you. Any questions about the derivation? Of course, once I have derived these particular formulas, I can forget about the Majorana basis. They are, of course, basis independent. However, in case you forget what's even and what's odd and you want to rederive it, I recommend you do things in a Majorana basis as I have done it. Where am I? I've got through this. Ah, yes. Charge conjugation has an interesting property in acting on the states of the theory that's somewhat reminiscent of the parity fact that a nucleon, anti-nucleon state has S wave, has parity minus. Oh, sorry, remark I wanted to make. We thus see from this that the two model theories we're looking at, the scalar and pseudoscalar interactions, psi bar psi phi and psi bar I gamma 5 phi, do preserve charge conjugation, providing we define the neutral scalar field to be even under charge conjugation. On the other hand, the sort of interaction which I suppose you know is encountered in electromagnetism, even though I haven't talked about vector fields yet, I suppose you know from classical electromagnetism, if nowhere else, that the electromagnetic interaction is J mu A mu, where J mu is the electric current and A mu is the vector potential. So assuming we have a quantum theory, as we will next semester, which involves a coupling of this form, where this is a vector field, this is charge conjugation invariant. Doesn't matter really. The vacuum expectation value vanishes by Lorentz invariance. This is charge conjugation invariant only if I say that A mu goes into minus A mu. That is to say, if I have such a quantum field, it has neutral particles associated with it, called photons. Since it's a real field, we'll call photons because it's the electromagnetic field. And the photon is odd under charge conjugation. A one photon state is multiplied by minus 1. If you wish to define charge conjugation in such a way that electromagnetism preserves charge conjugation invariance. This has interesting consequences for studying the properties of states. The most interesting states to study are, of course, states built up out of one particle and one antiparticle. States built up out of two particles are, of course, turned into states built out of two antiparticles by charge conjugation, and who cares what the phases are. But let's suppose I have such a two-particle state. Let me call it, I don't know what, psi. It's a good name for a state as any other. Integral sum on R and S. Integral d cubed p, d cubed p prime, FRS of p and p prime, some smearing out function to make it a nice normalizable state, BRP adjoint, CRS p prime adjoint, acting on the vacuum state. That's a nice two-particle state. Now when I apply charge conjugation to psi, I, of course, don't change any of this, which is just a C number, but I change a B into a C. And a C into a B. Now, these operators are in the wrong order for comparing the final state with the initial state, and I have to switch them around, which gives me a minus sign. This is still unchanged. That's the famous Fermi minus sign. And if I now use the usual game, since these are just summation variables, and I change r into s and p into p prime to redo my summation, I have sum on r and s, integral d cubed p d cubed p prime minus f s r of p prime and p b p r adjoint c s p prime adjoint on the vacuum. Thus, u sub c psi equals plus or minus psi, as one would guess, depending upon whether the smearing function, the amplitude, is symmetric or anti-symmetric. However, somewhat surprisingly, it is the anti-symmetric smearing function that goes with the state that's even under charge conjugation, the eigenstate with eigenvalue plus 1, and it is the symmetric smearing function that creates the state that is odd under charge conjugation, and really this is just a result of having to switch the two creation operators. Is the derivation clear to everyone? I will give an actual application. I will discuss positronium decay into two photons. Positronium, as I trust you know, is the hydrogen atom, except instead of a proton, there's a positron. It's a bound state of E plus E minus in an S wave in the ground state. As in our previous discussion of nucleon, anti-nucleon scattering, the annihilation, there are two S wave states available depending on the two spin states, J equals 1 or J equals 0. One is called orthopositronium and the other is called parapositronium. I think the J equals 1 is called ortho. Is that not right? Ortho means they're parallel. Para means they're anti-parallel. Anyway, I'll call them J equals 1 or J equals 0. If you have a positron captured by an electron, it quickly cascades down, just as in a normal hydrogen atom, to the S-wave state. However, the S-wave state is ground state is, unlike the ground state of the hydrogen atom, not absolutely stable because it can decay into gamma rays. The electron and positron can annihilate each other. Therefore, I will consider this decay into 2 gamma. That would certainly be the most popular decay. You probably also know that the electromagnetic coupling is weak, so you get an extra power of around 1 over 137. Actually, it's more typically 1 over 2 pi times 137 whenever you emit another photon in the probability, the square of the amplitude. Now, the J equals 1 state is a totally symmetric wave function. It is symmetric in spin and symmetric in space. Therefore, it is C equals minus 1. This, on the other hand, is symmetric in space, but anti-symmetric in spin. And therefore, it is C equals plus 1. Therefore, the process is allowed for this. Since the two photons have net C equals plus 1, they individually have C equals minus 1, whereupon the, and this is forbidden for this one, which must go into 3 photons, and of course does, but does so much more slowly than this one goes into 2 photons. So although both ground states of charmonium, I'm getting ahead of myself. Both ground states of positronium are stable, are unstable. The J equals 0 state is considerably more unstable than the J equals 1 state. Any questions about this application? The commutation relations of C and P are a little bit peculiar even for a free Dirac field, even with conventional definitions of the signs. If, for example, I take a one-particle state and apply first P and then C, I get minus the result of applying first P and then first C and then P. Because in one case, the parity operator acts on the nucleon operator, and the charge conjugation then turns it into an antinucleon, so we pick up the parity plus sign. On the other hand, first the charge conjugation acts on the nucleon operator and turns it into an antinucleon state, and then we get the additional minus sign from the parity. Likewise for one antinucleon states. Thus, in general, if I act on a state with an odd number of fermions in it, PC is minus CP, whereupon if I act on a state with an even number, including 0 fermions in it, PC is plus CP. This can be summed up by saying U sub C, U sub P equals U sub P, U sub C times the unitary operator associated with the rotation by 360 degrees about any axis. Since the rotation by 360 degrees about any axis multiplies every Fermi wave function, by every individual fermion wave function by minus 1, and therefore is plus 1 acting on states with an even number of fermions, and minus 1 acting on a state with an odd number of fermions. Is this hard to read? Did it get embedded in fossil material? Okay, now it should be easy to read. Is it clear to everyone? It's a perfectly legitimate symmetry operator. Any rotation, including one by 360 degrees, is a legitimate symmetry of the theory. So it's not surprising that it should turn up in the product of P and C. Now we come to the thing that is responsible for my flaked out condition this afternoon. We'll run a little bit over time. I see I'm going, because of all the errors I'm making, I'm going a little bit, and also because we started late. I will discuss time reversal. Or actually, now I worked it out just right. Where am I? God, I've got all of this material to go through. Oh, well, there's an awful lot of crossing out in it. I will continue. I will discuss PT, which is always easier to discuss in a relativistic theory, since the product of parity and time reversal commute with Lorentz transformations. I will continue using a Majorana basis. It's convenient. There is a connection between C and PT given by the CPT theorem, and what's source for C is source for PT. Now, again, I will begin by looking at the the scalar case and reminding you that there we had the fact that if box squared plus mu squared phi of x equals 0, that implied del squared plus mu squared phi of minus x equals 0. Now, we want to ask if there's a similar transformation in free Dirac theory does this imply that I d slash minus m, well, it's obviously not going to be psi of minus x, so I'll put in some matrix here, which I'll try and figure out later. The answer is yes, if we can cancel out the sign change caused by changing x into minus x with the matrix M. That is to say, yes, if we can find a matrix such that gamma mu m is minus m gamma mu. Now, of course, we have such a matrix. I saw eyes lighting up. It is gamma 5 or any multiple of gamma 5. And for purposes of making the CPT theorem come out right in the end, and not the I-CPT theorem, I will define the matrix, and most people do it conventionally that way, to be PT on the classical level. Psi of x goes into I gamma 5 psi of minus x. Note that for later purposes, since we're going to realize this by an anti-unitary operator, it is convenient to observe that I gamma 5 star is I gamma 5. It is a real matrix, and that gamma 5, we suspect that there is a anti-unitary operator, omega pt, such that omega pt to the minus 1 psi of x, omega pt equals I gamma 5 psi of minus x. Let me work out some of the properties of this hypothetical anti-unitary operator before I actually show you that it exists. Perhaps the most interesting property is what happens if we consider it square. Now, this is just doing the same thing twice. The I gamma 5 slips neatly through the omega pt, since it's a real matrix and the anti-unitarity doesn't affect matters. So I get I gamma 5 squared psi of x again, which is, of course, minus 1 times psi of x. Thus, omega pt squared is not the identity operator. It is an operator which must be a unitary operator, since it's the square of an anti-unitary one, and is an operator which, when applied to the left and to the right of a Fermi field, or its adjoint to one side, it turns the Fermi field into minus itself. We, of course, know such an operator. It's our old friend, as of 10 minutes ago, the rotation about any axis by 2 pi. You might think I have pulled this window, because you might say that minus sign is there just because you had I gamma 5 rather than gamma 5. What if you had gamma 5? Then you would get gamma 5 squared and would not get a minus sign. I will demonstrate that this is not so. Suppose I considered an alternative definition of PT. an arbitrary phase factor. I can certainly do that in the free theory. That's an internal symmetry, times I gamma 5 psi of minus x. Now when I attempted to apply another omega pt to get to minus 2 psi of x omega pt squared, I would now be able to bring the gamma 5 out through the external omega pt with no problem, the I gamma 5 because it's real. But the phase factor, of course, would get complex conjugated, because when I bring a number through an anti-unitary operator, it gets complex conjugated. Thus, I would have e to the I theta, I gamma 5, and from bringing the things out from the internal one, e to the minus I theta, I gamma 5, psi of minus x, plus x, which is, of course, exactly the same thing as before. If the square of an anti-unitary operator is minus 1, actually I didn't have to do it that way. Perhaps a better way would be to say, if omega pt prime is e to the I theta omega pt. Yeah, that's a better way. Omega pt prime times omega pt prime is e to the I theta omega pt, e to the I theta omega pt, which is, bringing this through this, omega pt squared. That's the same thing done more compactly. Thus, it's got a square of minus 1, and there's no way of fighting it by putting in a phase factor or anything like that. You can put in all the phase factors you want, and it will still have a square of minus 1 acting on or actually a square of this U operator acting on, sorry, it will still have a square, that's this U operator. Are there any questions? Now, I won't go through the full hierarchy of working out quadratic forms, because one of the homework problems has you investigating things like that, and I don't want to do the whole homework problem for you. But I will at least work out what happens to psi bar, so the homework problem won't be too difficult for you. It's known from the definition of an anti-unitary operator that if omega inverse A omega is A prime, where A is some normal linear operator, then omega inverse A adjoint omega is A prime adjoint. Therefore, let's apply this general rule to PT. Omega PT inverse psi adjoint of x omega pt equals psi adjoint of minus x times I gamma 5 adjoint. Now, gamma 5 is a Hermitian matrix. Its square is 1, not minus 1, so it's equal to its own adjoint, although it's not equal to its own bar. I, on the other hand, is of course an anti-Hermitian matrix, so this is minus I psi adjoint of minus x gamma 5. Now, let's look at psi bar. Beta, or gamma naught, omega pt. The beta is just sitting there, so we can drag it through the omega pt. It's just a numerical matrix, but it's an imaginary numerical matrix. We're working in a Rana representation, so we get an additional minus sign. Equals, switching things around once more, minus I psi bar of minus x gamma 5. So psi bar of x goes into minus I psi bar of x gamma 5. This is critical because it means, for example, such a friendly term as this, psi bar psi of x, will go under PT. This is, after all, a term that occurs in the free Lagrangian, and you would expect it to be nice PT transformation properties. Because psi bar has a minus I and psi has an I, we just end up with the gamma 5 squared, which is 1. So it goes into psi bar psi of minus x. To take another term that occurs in the free Lagrangian, psi bar I d mu gamma mu psi. There, if I apply PT, well, I'll write it out fully, if I can control the chalk. I get 3 minus signs. One from the I, an anti-unitary matrix, one from the imaginary matrix, one from gamma mu, an imaginary matrix, and one from just the fact that turning x into minus x changes the sign of d mu. So I get minus psi bar minus I gamma 5 I d mu gamma mu I gamma 5 psi, the whole thing evaluated at minus x. But now I've got to bring the gamma 5 through. When I bring a gamma 5 through a gamma mu, I change the sign again. So the end result is that this equals simply psi bar I d slash psi evaluated at minus x. As expected, both terms in the free Lagrangian have the same PT transformation properties. Otherwise, we would hardly expect the free theory to be PT invariant. Please notice the critical role of the I. Because this is an anti-unitary operator, the transformation properties under omega PT of I times an operator are opposite to those of the operator without the I. Bringing the I through the omega PT has a non-trivial effect. Thus, if one is writing down interaction Hamiltonians and wishes to check that they conserve PT, typically or P or C, typically the restrictions implied by P or C is that certain coupling constants vanish or equal to others. Typically the restrictions implied by time reversal or PT invariance is that certain coupling constants are complex conjugates or minus complex conjugates of other coupling constants. Now finally, not really finally, because I'm going to give a lightning proof of the CPT theorem, let me actually convince you briefly that I can construct a anti-unitary operator that does this job. Now, going along for the free field. I will take this equation and for convenience, I will replace x by minus x and put the I gamma 5 over onto the other side. Therefore, I have minus I gamma 5 omega PT inverse psi of minus x omega PT equals psi of x. That's the same equation. I'll check this equation by writing down the expression for a free field and seeing if it does the right things to creation and annihilation, does sensible things to creation and annihilation operators, and therefore will allow me to define an anti-unitary transformation on the one-particle states. psi of x equals, in a Majorana basis again, last time I'll have to write it in this lecture, thank God, UPR, BPR, e to the minus I p dot x, plus dot, dot, dot. The C terms will turn out to follow the B terms with no alteration. Now, let's do this thing. Firstly, I replace x by minus x. Secondly, I apply the anti-unitary transformation. That turns the p dot x back again to the right value. And finally, I apply the I minus I gamma 5. So this thing should equal integral, ditto, minus I gamma 5 UPR star, the unknown quantity we wish to compute, omega pt inverse, BR of p, e to the omega pt, e to the minus I p dot x, and evidently similar things for the C term. Okay, does everyone see that? I've just applied this operation to the expression above, saying it should be created. X going into minus x is canceled out by bringing it through the anti-unitary operator. U is complex conjugated because it is an anti-unitary operator, and there's the explicit minus I gamma 5. Now, let's check that this is sensible. It's certainly going to be sensible. There's certainly going to be some way of inducing a physical transformation on the B's if these objects, minus I gamma 5 UR star, are also U's. Well, of course they are, because we showed in our discussion of charge conjugation that complex conjugating turns a U into a V, that is, changes the sign of the P/slash term, but dragging the gamma 5 through the Dirac operator also changes the sign of the P/slash term, and the two minus signs cancel. So this is some other U. What other U it is depends on how you've chosen your bases and the phases of the U's, which I don't want to go through in detail. And therefore, it defines some reshuffling of the B's that defines the anti-unitary operator on the one-particle states, and those a fortiori on the many-particle states, and likewise for the C's. I won't bother to work it out in detail beyond this point, except to make one remark. If I take a state at rest that is, say, an eigenstate of LZ with eigenvalue plus 1/2, and look at complex conjugate this equation. L sub z, you recall, is a pure imaginary operator in Majorana basis. Therefore, this follows as the complex conjugate equation. I've just complex conjugated and used the fact that L sub z is minus L sub z. And therefore, L sub z also commutes with gamma 5, since it's even in the gamma matrices. And therefore, I get here minus 1/2 minus I gamma 5 U0 1 star. Therefore, the state, that is, if I start out with a state with spin up at rest, PT transforms it into a state with spin down. At rest, there is a sign change. This is, again, just what we would expect. It's reasonable that the combined result of parity and time reversal should not change the momentum of a particle. Because if I have a particle moving this way, I change the direction of time as moving that way, I make a parity transformation, it's back moving this way again. On the other hand, from non-relativistic theory, we know that parity does not affect the spin. Sigma commutes with parity. L does not. Sorry, L also commutes. Sigma commutes with parity. I'm falling apart. Sigma commutes with parity. On the other hand, time reversal, of course, changes the sign of the spin. If it's rotating this way and I run the motion picture backwards, it's whirling around the other way. And therefore, the combined operation PT should change the sign of the spin, and we found that it has. Any questions at this stage? All of these things are discussed with less elegance, but also with less errors in Bjorken and Drell. I would now like, I'm going to run, well, notionally 10 minutes overtime, but actually, since I started late, not overtime at all. I would now like to discuss the proof of the CPT theorem. It's not going to be too difficult because we already did all the hard stuff when we discussed it for scalar particles, where there we showed the CPT theorem was absolutely trivial. It was just a statement that replaced in every Feynman, at least in order by order and perturbation theorem, was absolutely trivial. It's not absolutely trivial to prove it rigorously. We just reversed the sign of all the momentum in any Feynman graph and observed that the Feynman graph was totally unchanged. And that was the result. That was the CPT theorem. Turned all four momenta into minus themselves. Every incoming particle became an outgoing antiparticle. Now, I would like to do the same thing here, but I would like to do it in a little cleverer way that will also indicate how this can be generalized to particles of arbitrary spin. For simplicity, I will consider a graph involving a theory of nucleons and mesons, perhaps not our theory, maybe some grotesque theory that doesn't obey parity, charge conjugation, time reversal, PC, CT, or CP. It's just, or TP. Just some messy, horrible theory full of epsilon mu nus and derivative couplings and God knows what. But at least for simplicity, I will restrict myself to a graph which has only one Fermi line going through it. That's just notational simplicity. You can see in words what's going to happen if I have 17 Fermi lines going through the graph. So I have this one fermion line going through the graph. From it, a bunch of meson lines come out. These mesons may have grotesquely complicated self-interactions. I don't care. And there's a bunch of momentum here on which I'll focus. P here. What do I call it? Q1, Q2, Q3 in this example, P prime. This has some incoming spinner U, and this has some outgoing spinner U prime. Now, the amplitude for this graph is going to be some god-awful mess, but I can certainly write it in the following form. A equals U bar prime, some numerator full of gamma matrices I run along the line. That's a function of P prime, Q3, ... P, and full of gamma matrices, U. And then there will be a real mess. That'll be the denominator that I'll call D, the Feynman denominator, full of I epsilons and inner products of things. And that's a function of practically everything in the whole graph, including everything that's in the question mark. And this whole thing is going to be integrated over all the internal momenta. Okay, that's the general form of a Feynman amplitude. Now, whatever we know about a Feynman amplitude, one of the things we know, no matter how grotesque the theory is that we are doing a Lorentz, whatever the Feynman rules may be, this has got to be a Lorentz invariant field theory. Therefore, this Feynman amplitude has got to be equal to the same thing with everything Lorentz transformed, all the internal momentum, all the external momentum, and all the spinors, in this case 2. And I should write a d bar here, but for reasons that will become clear, I'll write an equivalent expression, which is the inverse. And the denominator is also Lorentz transformed, each and every vector, although it's merely the act of a purist, and we integrate over all the internal momenta, of course. It's merely the act of a purist to write the denominator Lorentz transform, since the denominator is just a function of inner products. Now, now comes the cunning part. This expression can be analytically continued to complex lambdas. That is to say, to Lorentz transformations labeled by complex phis and thetas. Well, you say, analytic continuation. Ugh, that's always monstrous, difficult object. You've got to show that you don't encounter cuts, poles, essential singularity. Doesn't matter here. The denominator is manifestly analytically continuable since it's just a function of the inner products. It was merely taste that made me put the lambdas in there. The numerator is just a polynomial. The d of lambdas are, just combinations of gamma matrices, the 4x4 matrices that depend in an obvious analytic way on these things. All of the p mu's that are around are just sitting there. There's never any problem in analytically continuing a polynomial. So that's why I wrote a d inverse rather than a d bar, because, of course, the complex conjugate of an analytic function is not an analytic function, but the inverse is okay. So, therefore, at least if it's an exponential, which is what we're going to do, so there's no problem with poles, therefore, this can be continued to d of a of e phi, d with phi and theta complex. They're just exponential expressions. There's no problem in writing phi, a complex number for phi and theta. Is everybody happy? Does everyone agree that this is a perfectly legitimate, mathematically impeccable operation? This equation is proved for real phis and thetas, but I can obviously extend it, and it's evidently true by the principle of analytic continuation for complex phis and thetas. Well, what does it buy me? Complex phis and thetas give me something totally unphysical. Complex momentum, disgusting. May be useful in some other context, but not much help for proving the TCP theorem. However, there is a particular complex Lorentz transformation that is extremely useful, and I will consider it. And by doing the proof this way, by the way, you see how to generalize it to arbitrary spins. Let me consider the complex Lorentz transformation. That's a product of a rotation by 180 degrees about the z-axis by a real angle pi. Certainly a reasonable thing to do. I remind you that changes the sign of x and y and does nothing to z and t. And an acceleration, in order to make my signs come out right, I'll do it by minus 180 degrees, minus I, e sub z, pi. That is to say, a 180-degree rotation in the xit, zit plane. Just to show you what this particular acceleration does, let's work out what a real acceleration does. Turns P naught into P naught cos phi plus P3 sinh phi. and the similar equation for P3. Now, if I take phi to be minus I pi, the cosh of minus I pi is the cosine of pi, of minus pi. So therefore I get minus the cosine of pi, which is, I get cosine minus 1. On the other hand, the sinh of I pi is I times the sine of pi, which is, of course, 0. Likewise, P3, by the same reasoning, goes into minus P3. So this lambda is, in fact, minus 1. Lambda minus 1 is not a legitimate physical Lorentz transformation, but we can attain it by analytic continuation from real Lorentz transformations. Any questions? Therefore, I've successfully done what I did in the scalar theory. I have changed the sign of each and every momentum, and I've done something to the spinors, which of course I have to do because if I've got a U for an incoming nucleon, that's got to become a V for an outgoing antinucleon. What have I done to the spinors? What is d of lambda? Well, you recall at the very beginning of this lecture, I wrote down, in terms of gamma matrices, what represents these things. You've probably forgotten them because I have, but I have them written down here. For the rotation, I have e to the minus gamma 1, gamma 2, pi over 2. For the acceleration, because of the minus I have e to the minus I, gamma 0. I shouldn't have lowered them. Well, it doesn't matter in these quadratic forms, but gamma 0, gamma 3, pi over 2. Now let's work out what this thing is. Gamma 1, gamma 2 is a matrix whose square is minus 1. Therefore, the even terms in the series I really am going to run over time, but it's so beautiful and interesting, I don't think anyone minds. Gamma 1, gamma 2 is, I get, from the even terms of the series, cosine pi over 2. From the odd terms of the series, I get minus gamma 1, gamma 2, sine pi over 2. Likewise, I gamma 0, gamma 3 is a matrix whose square is minus 1. So therefore, I get cosine pi over 2 minus I gamma 0, gamma 3 sine pi over 2. Have I made a mistake?
Is there an I in there somewhere? When you go from the e to the minus pi over 2 sine?
Because gamma 1, gamma 2 squared is minus 1.
Yeah.
3 minus signs. So the even terms in this series have alternating signs, which is the sine power series for the cosine. And the odd terms in the series also have alternating signs, which is the power series for the sine. Okay. If you don't like it that way, I'll put in an I and an I. And then it's a matrix whose square is 1, and then it's a formula that's familiar to you. Now, cosine pi over 2 is known to its friends as 0, and sine pi over 2 is known to its friends as 1. So this thing is, with a little rearrangement, I gamma 0, gamma 1, gamma 2, gamma 3, or our old friend gamma 5. Therefore, whose inverse, by the way, is also gamma 5. Therefore, what we've shown is that our original amplitude, written this way, there's a little extra trick, because remember we had an I gamma 5 in PT, and I told you that was there to keep the conventions right. Haven't seen where that happens yet, but you will in a moment. Therefore, our original amplitude, defined there, is exactly the same as the amplitude, with here integral over all the internal momentum. Here are u bar gamma 5. Here a gamma 5 u. Here a numerator with everything minus. And here a denominator with everything minus. Okay. Please notice that because gamma 5 anti-commutes with p slash, this is an object that is interpretable as the Dirac wave function associated with an outgoing antinucleon. It is a negative frequency solution of the Dirac equation, gamma 5u, if u is a positive frequency solution. Likewise, this object, u bar gamma 5, was formerly associated with an outgoing nucleon and is now just right to be associated with an incoming antinucleon. It is the bar of a negative frequency solution. However, everything is not quite right, because this is not the amplitude for the CPT reverse process because of the Fermi minus sign. Remember, we did nucleon scattering, and we did antinucleon scattering, and we found nucleon scattering was a string of matrices like this, and antinucleon scattering was a string of matrices like this with a minus sign. To make the minus sign go out right, which is what we need. No. This is what the amplitude is equal. The original amplitude is equal to this, and this is manifestly the amplitude for the CPT reverse process. Because the amplitude for the CPT reverse process, antinucleon scattering of this bunch of mesons, is minus the string of Feynman matrices. This is the original, yes, that's right, that's cancels. I had an equality, and by multiplying by minus. And this object is now revealed as the amplitude for the CPT reverse process. Now, this whole thing, including all the minus sign, obviously goes through, if I had 72 nucleon lines going through, 72 antinucleon lines going through, a line with a hairpin turn going through. You can check it out, no matter how it happens. You always get a minus sign in the amplitude for the CPT reverse process. So the answer in the end is very simple. In any, absolutely any Lorentz invariant theory, you get exactly the same amplitude for a given process and the CPT reverse process, where the CPT reverse process means every incoming particle becomes antiparticle of exactly the same momentum, and as far as the Dirac spin variables go, every u for an incoming nucleon is replaced by I gamma 5u, which is a v, the appropriate object for an outgoing antinucleon. Every v for an outgoing antinucleon is replaced by I gamma 5v, which is the object for an incoming nucleon, a u. Since I gamma 5 is self-bar, likewise u bar is replaced by u bar I gamma 5. V bar is replaced by v bar I gamma 5. And that's it. It's all I gamma 5. Very simple rule. Just I gamma 5 everywhere. The reason it's I gamma 5 everywhere is because it's only one single complex Lorentz transformation that does the same job. It's always the same Lorentz transformation, so it's always the same matrix. The secret of the CPT theorem is analytic continuation to complex Lorentz transformations. And now if you happen to have a field theory of spin 3/2 particles on hand, you know how to derive the CPT theorem for spin 3/2 particles. Just compute d of lambda for this complex Lorentz transformation and insert an I because they're fermions. On the other hand, for spin 2, you compute d of lambda and don't insert an I because they're bosons. That's it. You tell me how it transforms under Lorentz group, I do a trivial computation and tell you what the right matrix that goes into CPT is. It's much simpler than either C or PT, and it's much more universal. Please notice also the form of the theorem is not there is a CPT operator with some unknown phase. We know what it is, and its phase is known. If someone comes to you and says, I have written a Lagrangian that is invariant under parity with the conventional phase, charge conjugation with the conventional phase, but in time reversal I have to insert an unconventional phase, you know that either this person has made an error or he has not written down a Lorentz invariant theory. Okay? That culminates this lecture, which ran phenomenally long over time, but I finally woke up at the end of it. And next lecture, last lecture before Christmas, I will sketch out how we do renormalization and such for spinor theory. Don't forget the homework set, Christmas present.
Well, I wanted to talk to you about the final exam, because that week I have